with that, let me introduce the first speaker, Andrea Santoro, from the Sentai Institute in Turin.
Okay, hello everybody. So I'm Andrea. I'm a researcher from Sentai Institute in Turin. And so today I'm going to present just a brief overview of the work that we've been doing basically in the last few years on topological data analysis and trying to characterize the higher order interactions. So in particular, why do we care? I think we can skip this, but the main idea is that has been a growing effort in the last few years about disentangling the behaviors and mechanisms in complex systems. And among all that we are interested here is basically trying to characterize this in the context of neuroscience. And one of the first papers back in 2006 was saying that basically what we can learn is that when we for instance, focus on the salamander retina, just pairwise model is enough to basically model a retina which is exposed to white stimuli, white noise stimuli, while this is not the case when the same retina is exposed to natural images. And this, over the last few years, has been, let's say, characterized in many different species, like monkeys and mouse, so just looking at the neural dynamics or local field potentials, and these group interactions, or higher-order interactions, have been characterized in cortical pulverization. So what I'm going to focus today on is the idea of this reconstruction problem. So in general, when you have a higher order signal, which in our case would be, let's say, a group of regions that are fighting together, or they are like co-activating together in a synergistic way, or let's say in a synchronous way, how can we move from having this kind of signal to something which is a higher order graph representation where not only here you encode the weights, let's say, of the different edges, but you also have group interaction, so which is what you see there as triangles fields or tetrahedron field. But the important problem that we have in neuroscience is that we don't have higher order signal, at least that we measure. We usually have something which is defined at the level of nodes. So how do we go from left to right? And has been a lot of effort, and the idea is that the key questions that have been trying to answer in the last few years is trying to reliably infer higher order interaction from this time series data. So think about MEG, EEG, or fMRI, for instance, and whether this kind of approach that models not only pairwise interaction like a network, but something more than that, can offer other classical pairwise approaches, and if so, can we get a better insight of brain dynamics? And so has been different branches, and I think today we are going to see a few of these like in these talks. So from information theoretic approaches, which are like, let's say, now more widespread, but they have on the other side the topological approaches. And then you have a few others, like based on tensor methods or machine learning techniques. And in particular, I'm going to focus on TDA. And why so? Because we are able to characterize the shape of group interactions in let's say, in a more mechanistic way. So what we start from is usually a multivariate time series. So for instance, fMRI bolts, which is extracted from single regions in the brain. And the idea is that we want to construct something which is the higher order generalization of a graph, so multiple interactions, where you have weights not only on the edges, but also on the faces of the triangles representing group interactions. And so we did a few years ago some studies, some research on trying to characterize these for like synchronous pairwise interaction or group interaction, and starting from the idea of edge time series proposed by the Indiana group, so Rick Betzel and colleagues. What we started from was trying to expand and move from node time signal to edge or triangle type signal, so everything which is trying to characterize the synchronies of two different regions together or multiple regions together at the same time. So imagine 3 different regions of the brain, you want to characterize how synchronous are their activity together. And to do so, basically they started to have new time series based on edges, for instance, so which is just the temporal wrapping of the Pearson correlation coefficient here. Don't look at the equation, but the idea is that you have just a point multiplication between any pair of time series. But then you can do the same for triangles, just to keep in mind that, like, let's say, when you have something which is odd, then you have problem of sign. Like, let's say, when you have something which is, the product of three negatives is negative. So we wanted to map this into have something which look at the coherence or the synchronous activity of these interactions. And so we mapped everything as positive, which was concordant, and everything else as negative. I don't go into the detail, but the main point is that you end up with a temporal simplicial complexes, which is just a generalization of a graph. And from there, you can use tools from topological data analysis to characterize the shape and the main structure of these, let's say, generalization of graph. And in particular, you can extract what is called using, let's say, persistent homology, the homological scaffold, or the violating triangles, which are just, if you think about it, it's more like those higher-order interactions. So imagine triangles as being triplets that are co-fluctuating or synchronous, much more than the combination of the different pairs making part of that triangle. And so starting from that, basically we extracted different indicators, some global and some local. And in particular, what we observed in the original paper was that using this kind of approach, we were able to, starting from synthetic time series generated from dynamical systems that are well characterized in physics, basically we could be able to, let's say, retrieve in a dynamic way. So on the bottom you have a synthetic time series, on the top our, let's say, one of our indicator, and as you go from left to right, so from order to disorder, you start seeing that this indicator on top is changing over time, trying to mirror like the differences in the dynamics of this synthetic time series. And these have been having some interesting application because at theoretical level, we see that this is actually more informative than any pairwise method. So let's say pairwise correlations, or also just looking up to edges. And so these you can see by looking at basically the amount of overlap that you have with this hypervariance indicator here is much less than, for instance, here. While if you know the higher order interaction and the specific position of the blocks, actually this is also true. So everything which is based on information theory is actually working as well fine. So apart from this, you can also look at how this mirrors in the brain activity. And in particular, what we observe is that triangles, so they always are, let's say, positioned in the somatosensory areas, as you can see from here, while scaffold, let's say, the scaffold structure mirrors somehow the higher order cognitive functions, so the frontoparietal and the MN. But do we really get some more information compared to classical techniques? And this is what we did in a follow-up paper just published last year in NatCom. And the idea was to try to see whether this kind of approach could provide information on task decoding, functional fingerprint, and brain behavior association. In particular, today I'm going to focus on task decoding just because it's for the amount of time that we have. And in particular, what we did was trying to start from a time series. We concatenated the different tasks, so rest plus different tasks from HCP data, so from working memory on the left up to gambling. And the main point here is that if you use, for instance, bold indicator, what we want to do is, let's say you have bold matrices for each subject, so n regions times t. Then you can do, instead of the classical functional connectivity approach, you can do a correlation between time. What I mean by that is just looking at the spatial profile for each time point compared to other time points. And so what you end up having is a time correlation matrix, which you can average across different subjects to have something which is unique for the entire session. And the main point is it's really good decoding the different tasks. Since I'm concatenating all of them, you should observe something that resembles a block design. So you have different blocks representing the different tasks at the central part. which should be representing the different tasks. And if we look at that, so here you can see the bold time signal. So as you can see from here, you start seeing some blocks, but then you have also some, let's say, similarities between of the off-diagonal part, similarity between different, let's say, tasks. But as you move from lower order to higher order, let's say, time series, you start seeing much better the patterns, I guess. And so you see here, you start seeing the different patterns from left to right. And what happens is that you threshold these matrices and you quantify how good you are at retrieving the different tasks. What you observe is that from lower order, so from bold time signal to scaffold time signal, you actually have something which is much more resembling the different block structure. Just some few works that we have ongoing. One is related to movies data. So we applied exactly the same approach to, let's say, emofilm datasets where you have different movies annotation about the different emotions, from discrete to any, like let's say, something which is physiological and so on, over 30 subjects. And what we do there is we don't have a ground truth, but we can try to retrieve what are the blocks that might be mirroring the activity of emotions. In particular, if we do exactly the same things, and we compare, for instance, bold versus scaffold, what we observe is a kind of a random pattern for a certain movie, for instance, here, for the bold time series, but when we move to scaffold, you start seeing a bit more temporal patterns, so similarity across different spatial organization. In particular, for instance, if you focus here, what we observe is that these actually link to one particular scene of the movie, which is the fight between the two main characters of the movie. And so the hypothesis is that the scaffold might be capturing temporal patterns having a similar level of emotions. So here, if you want to know more, we have a poster on Friday and Saturday on this. And the other just brief application that we have was just trying to get a lens of the higher order landscape. So trying to map what are the higher order approaches with the topological approaches and see what are the similarities and dissimilarities among them. In particular, just to pitch a bit, is that we find that topological approaches are well segregated. So here is the edge level similarity. So you're projecting all the measure at the edge level, and you're looking how similar they are, the spatial maps. These you can do at the nodal level. Here we did at the edge. And in particular, you see that the redundancies is all the different, let's say, ways of defining redundancy are all together with functional connectivity and triangles. Then you have something which resembles the scaffolds and homological part at the center and all the synergies on the bottom. The interesting part is, although they are very different, basically they align to the unimodal transmodal gradient, so the sensory association axis in particular. So just if you want to know more, we have a poster on this on Friday and Saturday. And just to conclude, of course, we have that TDA framework seems to capture something which is interesting about the temporal dynamics. We have that let's say, on synthetic time series, we can characterize different dynamical regimes, outperforming classical metrics, and then the scaffold actually tracks the cognitive states and emotional states. And in particular, it could serve as a bridge between redundancy and synergy that we will hear more in the next talks. And with this, I have a nonetheless extensive list of references, but I want to thank, of course, all the collaborators and the group interaction in these projects and the funders. Thanks a lot.
We have time for one question. Anybody?
Nobody use the app. I think I use the app.
In the app, there is nothing for the moment.
Okay.
No questions? Yeah, very rapidly. You hinted at this very quickly at the beginning. Can you say a bit more about the integration of the different measures? Well, not anymore.
Not anymore. No, so the integration of the different measure of like let's say the topological part, and so there is these things of different approaches, which one is related to, of course, higher order, let's say, mechanism that can be embedded using topological data analysis, and the other one, which is more information theoretic approaches and trying to characterize, for instance, the group interaction using information theory mainly.
Let's thank our speaker again. Our next speaker is Maria Pope from Indiana University.